I'm Clark Haskins. This is Todd Polino. We're SREs at LinkedIn. We run Kafka, Zookeeper, and SAMHSA for LinkedIn. And so why are you guys here? You want to learn more about Kafka, obviously, right? Or maybe you already use Kafka. I think a lot of you do. And you want to see how we run it. I think we have one of the largest installations in the world for Kafka. And we'll show you guys some tricks. Like I said, this is who we are. So SRE, do you guys know what that term means? Site reliability engineer. So yeah, we're basically the administrators. Yeah, it's right there. I was checking to see how many beers you had. So we're the administrators for the architects. We develop cool tools. Our goal is to keep the site running all the time. So here's Todd with the overview of Kafka.
All right. So some of you know what Kafka is already. Going to assume that not everyone does, though. So yeah, this isn't what we're talking about today, although this is still our logo officially. Well, no, we've kind of officially switched over. This is the new logo. If you haven't seen it, this is the Kafka logo now. It's no longer Kafka.
It's like chemistry meets a cake.
Anyways, so we're not talking about that guy today. So what makes up Kafka? Kafka is a publish subscribe messaging system. What does that mean? So in the Kafka space, we have brokers. That's what we call a server. It talks to Zookeeper because we store all of our metadata in Zookeeper, information about topics and brokers and consumers and everything else for now. We have producers and we have consumers. So all of our data is broken down into topics, which are broken down into partitions. So here we have one topic named A with one partition, 0. We don't like just one partition, though. One partition doesn't help us very much, and we'll see why in a sec. So now we have 2 partitions, and so our producer is sending messages into these partitions. So he sends a message gets stored in the Kafka broker, the consumer eventually reads it out. The consumer talks to both partitions in this case because we only have one consumer. If we had 2 consumers, one of them could talk to each of the partitions. So, but this doesn't work for us because we also want some reliability, we want some redundancy in our system. So now we have 2 brokers and we've split our partitions out. What this gives us is when we have our data, our partitions, so here we have A, partition 1, and we have partition 0 over here, but we've also replicated the data so that now whenever we write data into partition 0, it gets copied over to the other broker, vice versa. This way, when one of our brokers dies, the other broker can instantly take over and continue serving messages. The producers and the consumers rebalance as long as they're implemented correctly. And life goes on. When our broker comes back up, it doesn't do anything. All it does is start receiving the data again. So it doesn't take over again. It's not a situation where it suddenly comes back up and says, okay, I'm the master again, start sending messages to me. You have to actually do something, or you have to fail another part of the cluster for that to happen again. But this works out really well because now it means we have redundancy of our data, we have reliability in our system because we can lose a component and still keep on with life. So what is our Kafka cluster? First thing is it's disk-based. This is as opposed to a number of other messaging systems where messages are stored in memory, they're not retained for any period of time. Kafka is a log-oriented system. It's referred to by many people as a distributed commit log. Everything gets spooled out to disk. You can have retention for any period of time that you want. So we have durability. As you saw, we had multiple partitions. We had multiple copies of those partitions. So whenever we write our data out, we know it gets stored in multiple places. We don't have to worry about losing a broker and losing our data. It's also scalable. If we have more traffic into a topic, we just add more partitions. If we start maxing out one broker with network or anything else, Disk.io for example, we just spread it out, move our partitions. We move our partitions out to more brokers and we can handle as much load as we need. It's low latency. We're talking on the order, in general, of under a second propagation from producers to consumers. Usually less. When you start adding multiple clusters, that's where you introduce your latency. So usually you're talking about milliseconds, 10 milliseconds, 12 milliseconds. Messages move through the system very quickly. And you have finite retention. So you can configure your retention right now in 3 ways. You can retain messages based on time. So for example, most of our clusters, we retain data for a week. You can retain messages based on size. So you can say, I only want to retain a gigabyte of traffic, or gigabyte at any given time in this topic. You can also retain in key-based retention. What that is you have a topic and you write in a key, and every time you write a new message with that key, it replaces the old message, and there's a process that goes through and cleans things up. And this is fairly new for Kafka, and I think it seems to be working pretty well in the couple places we've got it going on at LinkedIn so far. The last thing is it's not idempotent. If a producer produces the same message into the system twice, that message gets stored in the system twice, it gets consumed out of the system twice. This says yet because that's actually a project that we're handing off to an intern hopefully this summer to work on adding idempotent messages. Of course, you can kind of do idempotent messages with the key-based retention already. So it's kind of there, it's kind of not. So how do we use Kafka at LinkedIn? We have multiple data centers and multiple clusters in each data center. We break things out by the type of data that we're putting in, and we do a lot of mirroring data between the clusters so that we can propagate data from one data center down to another. So we have it produced in the production data centers, for example, and then we propagate it back to our corporate environments where we may consume it for metrics or something else. We have multiple different types of data going through our system as well. We have metrics, as I mentioned, which is everything from operating system statistics like CPU, disk usage, memory usage, application statistics, call times for any particular part of our applications. We have tracking data, which is everything the users do on the front end of the site. Every single action that's taken by one of our servers is pumped into the tracking cluster, propagated back to Hadoop for processing, for reporting, and everything else. And then we have queuing between applications. We use this for sending emails. We use this for, just application discussions when you want to just get something off or pass it on to another part of your application. We were discussing with a few people that we're coming up with new uses every day for Kafka. Now one of our internal customers wants to use the queuing cluster to replace BitTorrent and send out multi-gigabyte files through Kafka. And we've talked about it. It sounds like a really neat idea, and they have a good idea of how they want to do it. We'll just see how well that execution goes. They have the reason they want to do it is because they've had some problems with BitTorrent, and they think that this will be a better solution for them. So you look questioning to that.
Incredulous, I think.
Yes, so did we, but it seems like it could work pretty well for them for the particular use case that they're doing. So, as I said, the tracking data, what we do is Kafka spends a lot of time transporting data to Hadoop. It gets processed, and then it gets sent back out to the production system. So, for example, users take an action, they look at something, it gets passed back to Hadoop, it gets processed by well, just lost the word. Anyways. It gets processed, it gets sent back out, so now the search results are updated. The things like people you may know and jobs you may be interested in are updated on the front end as that data propagates back out. The real difference in how we're running Kafka at LinkedIn is that we're running it as a service. It is a platform for the rest of the company to use. We don't really know anything about the data that's coming in or the data that's going out as the SREs. We're just responsible for keeping the system up and running all the time, making sure that it's available for everyone else. And when they come to us and say, we'd like a topic with 720 partitions, we say, wait a sec, why do you want 720 partitions? And we make them explain it to us, and then we say, oh, okay, we'll set that up for you. That was the discussion we had earlier today, actually. So why are we standing up here talking to you about it? And I'm going to warn you that everything on this slide is now a month old, so all the numbers are bigger. We have over 300 Kafka brokers, and I think the number's over 400 now. We've been doing a lot of expansion in the last month or so. We have over 18,000 topics in our system, and we have over 140,000 partitions, not counting replication of partitions, so double that number. We're doing 220 billion messages per day through the Kafka brokers in our system, and it's about 40 terabytes of data coming in. On the outbound side, we're doing 160 terabytes, and this is why we really love Kafka as a log-based retention system, because we're consuming out more data than we're putting in all the time. One of our favorite consumers actually reads out the data 60 times for every message that's produced in. They read out 60 times. This is not necessarily the best use case. We're having discussions with them about it, but it's what they're doing, and it's working for now. At peak, we're doing 3.25 million messages per second. It's about 5.5 gigabits per second inbound to all the clusters and 18 gigabits outbound. So again, always we're reading in a little bit, we're writing out a lot to our consumers. So I'm going to hand it back over to Clark at this point to talk about some of the other interesting things that we've been doing.
All right, so we've had lots of challenges running this at scale. So Kafka's still really young. One of the great things that we have the opportunity to do is we sit with the developers every day. So 5 of, I think, the 8 committers on the Kafka project we sit with every day. And so we're able to push them and say, hey, we need this feature. And it takes time for developers to get things rolled out. So we have to do some tricky things to make things not fall over before that new feature comes out. So one of the biggest problems we have is hypergrowth. So everybody all of a sudden wants more data. There's always more data, and it's always useful data. So we never delete data. There's always just ever-growing amount of data. So one of the cool things that came out with Kafka 081 is, so whenever you add a broker with Kafka before 081, whenever you added it, it wouldn't actually do anything. You'd add in the new broker, and it would just sit there and do nothing until a new partition or a new topic was created. But with 081, now what we're able to do is move partitions on the fly to that new broker. And so what we've been able to do is write a script that will take and look at the data size on disk and make sure that that's even across every single broker in the cluster. So these are all moving, while the cluster's hot. We've written that script. Another interesting use case we have is logging and metrics. So at LinkedIn, the logging and metrics go to the same Kafka cluster. So why is this an issue? Well, if a developer releases new code that doesn't work quite right, they start generating tons and tons of log messages, and it'll eventually kill the cluster. So one of the other cool things with the partition reassignment tool that we were able to do is we were able to essentially create a cluster within a cluster. So what this is what we call QoS. So we're able to move all of topic A onto a specific set of brokers. And so what we did is we moved all of our metrics topics onto a specific set of brokers that was not the logging set of brokers, so that whenever these things happened, we didn't lose visibility into what's going on across the site. Let's see. So we also had deployment nightmares. So with Kafka, as Todd mentioned, there's 2 replicas generally of every single topic. Well, if you have more than 2 brokers down at any given time within a cluster, you start losing data. Those partitions are offline. And so we were really scared to start doing parallel deployments. Or you couldn't do parallel deployments. And so what we were able to do is influence the developers to ensure that only one broker was ever offline at a time. So if we issued a parallel stop to the entire Kafka cluster, only one of the brokers would shut down, because before they shut down, they checked the health of everyone else in the cluster to ensure that they're up, they're functioning, and then one of them would be elected to shut down. So we did spend a lot of time babysitting sequential deployments until we got this new feature added. Yeah, we cried about it a lot. Now deployments are a lot easier. Make sure that the cluster's in a sane state before anything shuts down. Unless you kill mine it, then yeah, you kill mined it. So let's see. Already talked about that. So Zookeeper. So the way that the consumers work is every consumer is part of a consumer group. And what that allows you to do is parallelize your data consumption. So we have multiple partitions across all the brokers, and you could theoretically run the same number of consumers as you have partitions, and every consumer in that group, or the entire group, would only read each message once. All of that offset information about where each consumer is stored in Zookeeper. And as Todd mentioned, we have 18,000 partitions at LinkedIn. Topics. 18,000 topics. 140,000 partitions. And so each one of those has multiple consumers. They're all updating their offset data constantly. And so what this did is it overwhelmed their Zookeeper cluster. it couldn't handle the number of writes that we were pushing into it. So what we were able to do is we put Zookeeper on SSDs.
Problem solved.
And there's lots of conflicting information on the internet about whether or not this is a good idea or not. We did it. Our average latency went to 0 milliseconds. We were quite scared when we saw that.
Yeah, Zookeeper only has millisecond accuracy for the latency measurement. So everything just went to 0.
And we're like, is this thing still working? What's going on? And so, sure enough, it was working. Everything was great. And yeah, I think it's still average of 0.
Yeah.
So,
How many Zookeeper
It's never
clusters do you
0.
have?
how many Zookeeper clusters do we have? So each cluster that runs Kafka in each one of our data centers has, there's one cluster that runs all of the Kafka clusters. One Zookeeper cluster running all of the Kafka clusters.
How many replicas?
There's 5 nodes in the Zookeeper cluster. So. All right, so now monitoring.
All right.
Here's Todd.
So Kafka's used to monitor every single thing at LinkedIn, like I mentioned. All of the metrics go through Kafka. The backend systems that do all the graphing and all the alerting read that data out of Kafka in our corporate environment. So every single application, every single server has multiple touches to Kafka in our environment. So this makes it very sensitive as an internal data product. So, almost every single day, someone comes crying to us. Kafka's broken. So I know some of you have daughters. I know some of you know that this is Pinkie Pie, because I have 2 daughters, and that's how I know it. And I know that you know that Pinkie Pie's always happy. Our Kafka consumers are always happy because we transport all their data around for free. They don't have to do any of that work. So why is she so cranky all of a sudden? Because Kafka's broken. Everything's Kafka's fault first. So everything touches Kafka. So whenever anything breaks, whenever there's any exception in the log files, if it even remotely mentions Kafka, all of a sudden it's our fault and we have to get involved and figure out what's going on. And this is why we're on call, and this is why our developers are on call, because either we're going to look at it and determine that there's a problem with the Kafka servers, or the developers are going to look at the application and determine why that particular application isn't using Kafka properly. But really what it comes down to is almost always the consumer problems are with lag and rebalance. So what's lag? Lag is the difference between where the Kafka broker is as far as messages, which we call the tail, the end of the log, and where the consumer is with reading messages, which is generally somewhere further back than the tail. So that difference between where the consumer is and where the broker is our lag. So why is lag a problem for us? It's not really. It's a consumer problem. It's their problem. Their application is slow. They're doing too much garbage collection and they're falling behind, or they're losing their connection to Zookeeper or Kafka or something else. They've implemented their consumer incorrectly. They brought up 6 servers in parallel, and they suffered 5 sequential rebalances of their consumers. As each one came up, it caused the consumer group to rebalance once again, and then they hit their limit of 5 rebalances, and their application panicked on the 6th time and said, "Oh, I can't start up," and it fell over and died. These all come back to consumer issues. So, we have to educate our users as to how to use Kafka properly. So they just want to write their data in and get their data out. But we have to help them use it properly. We have to teach them what to monitor about their application and what to look for in the logs. And this is why our developers spend a good bit of time looking at other people's log files and determining what a particular error message means. Now, errors with the application generally come down to application problems, as I mentioned, GC, long processing times, or sometimes it's a Kafka client problem. There are bugs in the Kafka client. We will freely admit that. And then we hand it off to the developers and let them figure out what the bugs are and fix them. So sometimes it is, in fact, something of a Kafka problem. And every once in a while, it is an actual Kafka problem that we have to fix the broker because the broker fell over and died, or the cluster's being slow. So if everyone's calling us constantly, how do we end up sleeping at night? Because we're the ones who are on call. We're the ones who have to respond to all of these things. As I said, the first thing we do is educate our users. We teach them what lag is, how to monitor it, and how to resolve it when it's an issue, what to go looking for. Mostly we teach them why lag is their fault and not ours. We're also spending a lot of time monitoring our system. So we want to make sure everything's healthy, because the first thing that we need to do whenever somebody comes to us with a problem is go in and look at the Kafka ecosystem and say, yes, our system is healthy, everything is working properly. So let's go look at your application and see what might be going on that side of things. This means we're monitoring the Kafka brokers, we're monitoring Zookeeper constantly, we're monitoring our MirrorMakers, which if you don't know what MirrorMaker is, I'll get into it in just a minute. We also have an audit infrastructure, which I'll also cover along with the MirrorMakers, that helps us assure all our data is getting where it's supposed to be. And then we have REST interfaces to Kafka as well for those users who either can't or don't want to use the Java client for one reason or another. The other thing that we're looking at, in addition to the metrics at any given time, is we're looking at our week-over-week metrics. So we compare everything we're doing this week to what we did last week, so that we can watch organic growth over time and know when we need to expand our clusters. We can also know that if we had a spike in traffic last week at 10 o'clock on Monday, and we had a spike this week at 10 o'clock on Monday, and maybe 3 weeks ago we had a spike at 10 o'clock on Monday, that might be normal. And so we don't really need to be concerned about that particular alert if that's a normal state of being for us. So when it comes to the Kafka brokers, what are we looking at? The one thing that you need to monitor, if you're monitoring nothing else about Kafka, is under-replicated partitions. This is when you have a broker down, or otherwise you have two replicas and one of those replicas is not available for some reason. This means you're running your cluster in a degraded state. You can see a couple different types of things with under-replicated partitions. You might just see the numbers spike up and then drop back down immediately. That generally means you have a load problem. You got a spike of data into the cluster, you maxed out a network interface, and so you'll see partitions go under-replicated and then they'll go back. But if you see a bunch of brokers in the cluster that all have a high under-replicated count, then you probably just lost a broker and you need to look into why you lost one of your servers and get it back up. As long as you have under-replicated partitions, so we run with replication factor 2. That means we always have one copy of every partition, one extra copy of every partition. So if we see under-replicated partitions, that means we can't lose any more servers than that. We can lose one server. Once we lose one server, we're degraded. If we lose a second server for some reason, then we have offline partitions and we're losing data out of our systems. Data can't get written in, data can't get read out. So we're monitoring offline partitions, but if that number's ever anything other than 0, we have a serious problem. We want to catch it at the under-replicated state, not at the offline state. We're also looking at the number of partitions that each broker has. As Clark mentioned, we wrote a script to actually level the number of partitions on each broker. So it's not quite as simple as just the count. We want an equal number of partitions, but really what we want is an equal amount of data across partitions. So the data size on disk is actually more interesting than the broker count is. So we're looking at that as well. We're also looking at the number of leaders that each broker has. This is, so as I mentioned at the top, you have replicas. If you're not familiar with Kafka, then you might be a little confused when we talk about leaders, because only one broker is ever the leader for a given partition. So you may have two replicas, but only one broker is actually talking to the consumers and producers. You can't read data out of the other replica. You can't write data into the other replica. All you can do is copy data over to it in case there's a failure. So we want to know that our leader count is balanced across all the brokers, because that means each of our brokers is getting about the same amount of load. And there is an automated feature to automatically rebalance the leaders in the partition whenever they go out of whack. Doesn't really work that well at this point. So this is a task that we have to do manually if things get out of whack. And then we look at our network utilization. As I said, if we max out a network interface, you start to see under-replicated partitions. So this is a situation we want to avoid. In general, we don't run anything else on the Kafka brokers, so all of the traffic through the network interface is due to Kafka. And if we're maxing things out and if we're doing it on a regular basis, then we need to add more brokers to the cluster to add more capacity across the board. Monitoring Zookeeper. This is the other thing that we have to look at. Both the brokers and the consumers, for now, talk to Zookeeper. So in general, Zookeeper is a fairly simple thing to operate. We want to know that the ensemble is available. Just anyone who doesn't work with Zookeeper, an ensemble is what you call a cluster in Zookeeper. Somebody didn't like the word cluster, so it's an ensemble. So you want to make sure that your ensemble is available. So if we're running 5 Zookeeper nodes, we need to have at least 3 of them. We need to have a quorum of at least 3 Zookeeper servers. So we lose one, we can only lose one more before the Zookeeper cluster is in danger of being unusable. And since we're talking to Zookeeper and everything's talking to us, that's not a good situation to be in. Looking at the latency, it's tough. It's very hard now monitoring a stream of zeros, but we do it. It should always be 0. Our outstanding counts as well, because Zookeeper processes requests serially. One request comes in, it gets handled, it gets sent out, the next request gets processed. If we have outstanding requests, it means things are backing up for some reason, and we need to look into why things are backing up. There's some processing problem. Brings us to MirrorMaker and audit. So here we have a simplified view of our Kafka cluster. We have a producer who's writing messages into our cluster. What MirrorMaker does for us is it allows us to replicate data from one cluster to another cluster. And we use this for propagating data between our data centers. We use it for propagating data back to our corporate environment where we do processing or we look at the metrics or whatever else we're doing. We spend a lot of time copying data around our system to the point that we probably have more traffic in MirrorMakers than we do in actual applications producing data into the system. So what do we monitor with MirrorMaker? We monitor the lag. And I know I said that lag's a consumer problem, but in the case of MirrorMaker, it is consuming the data out of one cluster and producing it into another. So as a good Kafka user, we monitor our lag. And we keep an eye on what's falling behind, because if this lag on this starts to increase, it means the data's not getting to this cluster, which means our monitoring applications aren't going to work for some reason or another. And Hadoop processing is going to stop, and our executives are not going to get their reports. And when executives don't get their reports, they get cranky. And when executives cranky, we get emails and we get phone calls, and it's not a happy situation for anyone involved. We also monitor drop messages. Our goal is 0 drop messages, and that's what our alerts are all set at. If anything goes over 0, we're losing data out of our system as we transport it back to Hadoop and back to our metrics system. Now, it may not be as important on the metrics side because we can lose a message or two and we still have an overall view of the system. But when we lose tracking data out of the system, we're losing money. Tracking is what our users are doing. It's ad impressions. It's emails into the system, it's emails out of the system. Everything goes through the tracking cluster. So that's where we start losing money, and we have to keep an eye on it. Which is why we also have an audit system structured around Kafka. The audit is a piece that is custom to LinkedIn. It's not part of the open source stack at this point, although there is talk about open sourcing it as we can. What the audit consumer does is every producer, in addition to the messages that it's writing into the system, is also producing messages into a special topic about how many messages it produced. So over a 10-minute window, it will send a message into this topic that says, I sent 100 messages into topic X over the last 10 minutes. So all of that data ends up in our Kafka cluster, and it also gets mirrored as part of our MirrorMaker strategy. And then we have this audit consumer that reads from every cluster. And what it does is it consumes every single message out of the Kafka cluster. And it calculates counts on how many messages it sees in each topic. And it writes data back into the same special topic that says, over this 10-minute period, I saw 100 messages in topic X at this cluster. And the audit consumer at the next cluster down does the same thing. It reads all the data out of that cluster, and it writes counts back in. And all of this data gets propagated through the system. So what are we monitoring with our audit consumers? So I haven't hit the interesting part of audit yet. But with our audit consumers, we monitor lag. They're consumers. We have to make sure they're up to date, because if they fall behind, then all of our tracking information falls behind as well, and we don't know how many messages got produced. We're also doing a completeness check on the data. This is where the last part of the audit system comes in. So at the lowest tier of Kafka, we have an audit UI. It reads data out of all of the clusters. So it reads data out of this cluster. It also reads data out of every other cluster at Kafka. The only topic it reads is that special tracking, that monitoring topic. So it's reading all of the counts. It's reading everything the producer said it wrote in, everything the audit consumer said it saw. And it puts all that data together and generates us nice, pretty graphs that show for each tier how many messages there were in each topic over any given period of time. It shows us the percentages of how much data got through. So it's looking for, the producer said it got 100 messages, the audit consumer here said it got 100 messages, the audit consumer here said it got 99 messages. Oh shit, we have a problem now. So now we have to go back and find out what happened to that last message. And if that number ever drops below 100%, we get emails. We get emails, the developers get emails, the Hadoop ETL team gets emails, because that stops the Hadoop pipeline from working properly. But really what we end up looking at is nice pretty graphs that show our topics and the period of time, and we can see here that one of our clusters is dropping off as far as event counts. In this particular case, we have an audit consumer in that cluster that's falling behind because it's under capacity, and so we had to resolve that situation. We also get nice information about how long it takes to load our data through the system. So all of our clusters are sitting here down at the bottom right around 11 minutes, 10, 11 minutes, because there's a 10-minute granularity in the system. And then this one cluster shot up to 233 minutes at one point because it was getting its data very slowly. But this helps us assure that all of the data gets through our system, and it helps us assure to everyone else that, yes, you're seeing every single message that was produced into the system, and you're getting all the things that you want to see. So, now that I'm done talking about monitoring, we can monitor our system so we know that it's healthy. So how do we make sure that it's running at peak performance? Kafka's a pretty stable application as far as things go, and it's fairly good at doing what it does. It processes the messages through the system very quickly, and there's very little tuning that you have to do past the defaults with Kafka. Until you start getting into some weird situations, and we're starting to look at some, tuning I/O threads and other things, but once you get it running, it just tends to work properly. So really, we're talking about hardware and OS tuning a lot of the time, and we're talking about Java tuning. And that's generally what it comes down to. So with the hardware and the operating system, we start with our kernel tuning. There's not too much to do. The biggest thing is you don't want to swap. You never want to swap. Swapping is bad. Swapping will instantly slow down Kafka to a crawl. Then your data doesn't get through the system. Nobody's happy. Now, there's an interesting note to this. So we set swappiness equal to 0 on all of our servers. However, we just found this out recently that in Red Hat 6.4, they changed the meaning of swappiness equals 0. Swappiness equals 0 used to be a request to the kernel that says, please don't swap. Just don't do it if you can avoid it. But it would still swap if it had to. If you started to run out of memory, it would swap to disk. No longer. In 6.4, swappiness equals 0 is a demand. Yes, exactly. Because what happens is if you run out of memory, it will not swap. It will instead OOM your processes. This is not a happy situation for Kafka or really any database or anything else that you're trying to get data through. So we're now switching all of our servers over to swappiness equals 1, which basically it's a scale of 0 to 100 as far as how likely it is to swap. So it'll be 1% likely to swap instead of 0% likely to swap. But the difference is that at equals 1, it's still a request. It's not a demand. So that is an interesting thing to note. One of the other things we do is we allow more dirty pages in memory. We've got lots of memory on our servers. We are using most of it in page cache, so we let the dirty pages build up. But we allow less dirty cache in the system because we really want that cache to be available all the time for us to use. We're doing a lot of disk I/O. We're doing a lot of network I/O. So disk I/O, that's the other big thing that we have to worry about. We're flushing everything to disk constantly. So the biggest thing that you can do for your disk is more spindles. We actually run all of our Kafka brokers with a RAID 10 of 14 disks. So we get as much performance out of those disks as possible while still having a little bit of redundancy built into them. And we allow a longer commit interval on that mount point. So whereas the normal kernel commit interval for an ext3 mount point is 30 seconds, I believe, between flushes, we actually set it to 120 seconds. The reason that we do this is because we can tolerate losing 2 minutes worth of data if the system crashes, because we know it got written to another one of the Kafka brokers. So when that server comes back up after a crash, it's going to have to recover all its log files anyways. So we'd rather squeeze out the extra performance by extending those commit intervals a little bit more.
Are you using BBU or flash cache for your RAID?
We are using, yes, there is cache on the RAID and they're battery backed up, so that we get that last commit, but the disk won't flush from the kernel to the RAID for that last bit. So if it gets to the RAID card, it's fine. But if it doesn't get from the OS to the RAID controller, then you're going to lose that bit there. So there's still going to be some in memory that doesn't actually get flushed to the RAID controller. So the other side of tuning Kafka, tuning the system, is tuning the JVM. And really, when we're talking about tuning the JVM, we're talking about garbage collection. Now, eyes glaze over when we start talking about tuning garbage collection, because to most people, this is a dark art. It requires sacrificing small animals and arcane rituals and knowing all the little things to poke and spending months and months tweaking parameter after parameter until you find just the right combination of flags that gives you the optimal performance. And then your workload changes and you have to do it all over again. We skipped all of this. So recently we moved to Java 7, update 51. And life has been wonderful for us. We stopped spending any time whatsoever on tuning because what we got was the garbage first collector. For those who aren't familiar with this, the garbage first collector is designed to take all of the joy out of tuning the garbage collection on the JVM. Garbage first tells you, look, just tell me how much memory I have to work with, tell me how long you want your GC pauses to be, and leave me alone. Don't set sizes for anything. Don't try to tweak anything else. Just let me figure it out. And it's actually pretty good at it. So you set the heap size. We actually set our heap size to 4 gigs now. You specify a GC pause time. This is the target time you want. It's not a guarantee. You're asking the JVM to please try and hit this target. It should be reasonable. Otherwise, you're going to spend all your time in GC. We specify 20 milliseconds for ours, and we're hitting that pretty consistently within a millisecond or two. And you don't set anything else. So it used to be you would set the new generation size. If you fix the new generation size in G1, you override the pause time target, so it doesn't really help you very much. So what did we see when we switched to G1 collector? And I'll tell you that we did this over a week when our boss was in Hawaii on vacation. And he was reading emails, wondering if we knew what the hell we were doing as we were rolling this out across the board. And it all turned out for the best. The biggest problem we thought we were going to have was moving to Java 7, and we actually did not have any problems with Kafka under Java 7. So what did we get? We spend less than 15 milliseconds per second in GC. And I said our pause time target is 20 milliseconds, so we're doing less than 1 young GC per second now. More importantly, we're seeing steady 20 to 22 millisecond GC intervals all the time. So we can count on what our GCs are going to be across the board. And we know it's not going to slow down our application significantly. And the most important thing, we don't see any more full GC cycles at all. The only time we see a full GC on a Kafka broker is if someone really drives load into the system and it usually overloads the network interface. Then we will see one full GC on a broker or 2 within the cluster, and then it goes back to normal. Yes?
Quick topical question to this, but not necessarily to Kafka, but are you able to actually monitor how much of that heap is being consumed so that you have some sort of advance warning that you're about to exceed your request, or is the only way that you know that you exceeded it the fact that you start blowing your pause times?
No, we actually do monitor the memory usage and the GC statistics of the broker. So the way we run a lot of our Java applications is they're run within a Jetty container. And the Jetty container is actually instrumented for us. It's one of the nice things that we get as part of the LinkedIn deployment system. It's instrumented, so it will pick up all of the metrics from the application that's running. It will emit to Kafka all of our metrics about how long our GC intervals are, how much memory is in use, how many GCs we saw, both young and old. It also picks up all of the application statistics and exports those. So some of the things that we monitor are both the amount of time we're spending in GC, the amount of heap size that's a heap that's free within the system. So we're keeping an eye on that, because if it starts to go up, then we're going to have a problem. We actually went through a cycle of running update 21 for Java 7, which I do not recommend doing it. There were significant improvements to G1 as of, I think, update 23 or 25, and 51's even better. But we actually had some significant problems, which we saw manifested in those statistics when we were running it.
You still have to set your heap size though.
Yes,
How
you
are
can.
you picking your, I mean, that's the most, how are you picking that?
We're looking for, so the big thing we were looking for with the heap size and why we went from 3 gigs to 4 gigs is because we were trying to hit that target. So we set the target at 20 milliseconds, but with the smaller heap size, we weren't quite hitting it most of the time. So we just played with, since we only had 2 toggles to play with at that point that we were really supposed to be playing with, we set the target time at 20 milliseconds. We thought that was a good time based on what we had seen with par new before that. And so we bumped up the heap size a little bit on top of that so that we saw it hitting the goal. The nice thing about G1 is that it handles larger heaps much better than previous garbage collection, because it breaks it down into smaller processing pieces.
But one of the things to point out is it's really useful to leave the rest of your memory alone so that you can use your page cache, because that's where Kafka really starts screaming in terms of performance.
Yeah, so to that point, our brokers are running with 64 gigs of memory. And the only thing running on a Kafka broker is Kafka with a 4 gig heap. Everything else on the system is used for page cache. It's used to handle the disk I/O and the network I/O and make sure things flow smoothly through the system.
Is the new GC, you're using Oracle JDK, or
Yes.
using Open? Do you know if it's an Oracle only feature, or is it?
I don't believe so. I think it's in OpenJDK as far as I know. I'm pretty sure it's OpenJDK is essentially a feeder for Oracle's JDK in ways, the same way Fedora is a feeder for Red Hat features. So it's almost 100. I'm almost 100% sure that it's in. You'll probably see more stuff, more features added in OpenJDK before it makes it to the actual Oracle JDK.
Right.
All right, so in closing, so 082 is coming out relatively soon. One of the things that the development team is doing is they're moving the Kafka offsets for the consumers to be stored within a specialized Kafka topic, rather than being stored in Zookeeper. We had lots of issues with Zookeeper. SSDs, were essentially a midterm solution. This is the long-term solution, so everyone will benefit from it very soon. Delete topic. Currently, there is no way to delete a topic without shutting down the entire cluster all at once and removing it. It's a royal pain.
And
We've had to do this.
We have, but one note, there is an actual delete topic command in 081.
Don't run it.
Don't run it. Please do not run it. It was actually disabled in 0811 because it does not work properly.
It doesn't actually just not work, it destroys the cluster.
It has a very high likelihood of destroying your cluster if you try that.
Did you learn this the hard way?
More than
Yes.
yes.
Thankfully in our staging environment.
Yeah, and we didn't run it. Another SRE at LinkedIn ran it, and yeah, it was a mess. Okay, so further down the road, we have a new producer coming out. We're actually starting to test it now. It has higher throughput and an improved API. It also, rather than batching messages based on the number of messages in the batch, it batches based on size, which is a whole lot better, so you don't ever exceed your broker maximum message size. Then upcoming operational work. So we failed kindergarten, trying to relearn how to share, and you know that server's not going to come back online for a number of days or weeks potentially. So what you're able to do is move all of the partitions that were assigned to that broker to other brokers and get the cluster back in a healthy state while that broker's offline. We're working on the script for that right now. We're also writing a cluster comparison script. So as Todd kind of showed you, we mirror our data everywhere. So one of the big issues we run into is each topic has its own configuration in terms of the retention, whether it's size-based, time-based, the number of partitions that it has. There's lots of different attributes for every single topic. And we might set it on one cluster and then that data gets mirrored to the next cluster. Well, if we don't set it there, it never gets set. It just takes the default values. And so that's one big problem for us. So we're writing a cluster comparison tool to make sure that for any given topic, it has the same configuration across all of our clusters. Then advanced monitoring. So one of the big issues we run into is all of a sudden some producer will start sending us a ton of data. And we can see the data increase on our graphs. The cluster's taking a whole lot more data. Figuring out which topic that is pretty difficult. So what we're going to do is we're going to try and figure out how to monitor input size over time. So compared to the last hour, the last 2 hours ago, just to see what the increase will be. How can you guys get involved? You can go to the Kafka webpage. You can join the mailing lists. We're on IRC. Contribute tools, become a committer. And then you can talk to us. Here's our contact info. We're both on LinkedIn, imagine that. Find us there.
Thanks.
Thanks.